Hey, Cyprien here from F here for All, and today we're gonna do a second tutorial of Salome CFD, and I'll show you how to build this model, the Shear Driven Cavity Flow. So you have basically a cavity here which is a square, and which you have three walls, you have some water inside, and the top wall is basically moving in the X direction. And you want to calculate what is the steady state of the water inside this cavity following the movement of this plane. So it looks like a 3D model, but it is actually a 2D model. It's because for Code Saturne, the solver of Salome CFD, you have to build a 3D model with one layer of elements on the thickness in order to calculate this kind of 2D model. Okay, so without talking too much, let's go into the tutorial. And just before, maybe some of you didn't watch the first tutorial, so you don't know how to install Salome CFD. So of course, if you want to follow this tutorial, you have to install it. So let me just tell you briefly. You have to head up to codesaturne.org website, on which you have Salome CFD here, and you have a link here, download on the Salome website. So click on here, and this will bring you to this page where you will find here download Salome CFD. So I'm using the second one because I know this one is working on Ubuntu, and I'm currently using Ubuntu 16.04. I think it should be working on Ubuntu 18.04 as well, but you might need to, I don't know, install some additional libraries or stuff like that. Okay, so now let's just start the tutorial. So I close this one, and I just open a new Salome CFD window here. So let's put it in full screen. Let's open a new project, and you see you have a bunch of modules here. That's all the modules which are included in Salome CFD. So let's click on geometry. And let's build the geometry of my cavity. So this is extremely simple because the only thing you have to do is create a box like that, and this will be in X and Y direction. This will be 1 and 1, and Z direction will be 0.1. Apply and close. Now let's put that. Let's click on this button to reset the view. The other thing I need to do is to basically create some mesh groups that I'll be using to assign the boundary conditions. So to create mesh groups, I need to create mesh. To create mesh, I need to create the geometry, and I need to create geometry groups first. So this is my geometry. To create geometry groups, go here, group, create group, and we'll basically have to create some groups for all the faces. So let's create one volume group for the full model. I don't remember if this is really needed, but better to have that. Okay, let's select this, add this. So this will be volume. I'm not sure I really need this one, but better to create it first, otherwise you may have to come back several times. Okay, now the moving face, the moving wall is the top face. Add that, and you can call it moving wall, for example. Now let's there's three other walls. This one on this side, and the one on the bottom. I will put them in one group. So those will be simple walls, stationary walls, maybe you can call it if you want. Apply. And they are the two phases, because this is 2D model, I told you. So this face here and the face on the other side will be symmetry faces. So I'll just call them symmetry group. Apply and close. Okay. Now, in order to do the meshing, I'll need to have some edge groups as well. So to create edge groups, there is a function here in operation block called propagate, and if you do that, you see that it automatically creates 3 kind of compounds which contain the edges of my model. So this, in this direction, this is the X direction group. So it's better to rename them. So I'll just, because it's easier afterwards. So this is X direction, this is the Y direction, and the last one, well, it's the Z direction. So I'll just call that X dir, Y dir, and Z dir. Okay, and now my geometry is complete. So let's head up to the S-Mesh module to have this model meshed. So you have nothing. The first thing to do is to click on your box and click on Create Mesh. And now I have to create some mesh from that. So the first thing is to choose the algorithm I want to use, and this is a simple box, so I'll use this hexahedron IGK, which will map the mesh with hexa elements, and I have to define this for all the dimensions. So for 2D I use the quadrangle mapping, for 1D I use Y discretization, and I'll give it local lengths of 0.14, apply and close, and let's just mesh that first to see what I get. So right click, compute. Okay, it doesn't show me the mesh, or maybe because it's too small. So reset that, reset or zoom in. Okay, now that's what I get. So this is much too coarse. What I want is to really so one element in the thickness is okay, that's what I want, but I want more elements in those 2 directions. So for that I'll just create sub meshes. So click on create sub mesh, and here I need to select the geometry, which are, so that's when you use those groups that you created. So my submesh are X dir and Y dir. So I create one first for X dir, Y discretization, and I'll put a number of segments. Let's use 15 first. Apply. And now let's do the same for Y direction. Apply and close. Let's remesh all that. Compute. Okay, now I get a mesh which is better. Okay, so now what you need to do for next step is to create some mesh groups that will go along with the geometry groups that you created previously. So to do that, it's actually pretty easy. You have a command create groups from geometry. So use this, select those groups, and apply and close. Now to be able to do that, those groups have to be subshapes of this geometry. If those are not subshapes of this geometry, well, it's not gonna work. There are other methods like filters and stuff like that, but anyway, that's going to too much advanced things for this tutorial. Okay, so I have now 3 groups, so let's have a look. So this is symmetry group. Always good, you know, to check that the groups you created corresponds to what you want. Sometimes you have some surprises. Okay, so my 3 groups are okay. And what you need to do next is to actually to export this mesh. So we need to export those data into a MET file. It's better to create one folder where you put all your projects. So you see I already done it once, so this one will be cavity 2, and I just save that one into this folder. Now as I already done that, I know that this mesh here is a bit too coarse for this model, so I should actually use 50 instead of 15. So in order to do that, you can open like that the applied hypothesis, local lens, right click, edit the hypothesis. Oh, okay, this is the general. Let's go on the submesh. Yeah, number of segments. Okay, edit that, and you want 50, sorry, 50, and now you can remesh, recompute, I mean. Okay, now I get much finer mesh. And when you do that, there's one thing you don't need, don't forget, is to re-export the mesh, because sometimes you change the mesh size and then you go in the CFD module, you compute again, and why the result doesn't change, and it's because you have basically to export again the mesh. So don't forget this step, export, med, save, and overwrite the mesh. Okay, and now my mesh is completed. So next step is to go into the CFD part. So CFD study. Now this CFD module, well, sometimes it has some glitches, so you'll see that. Okay, so you'll see that sometimes the menu resize, they replace themselves somewhere else, you don't know what happens. So if you see this kind of thing, well, don't be surprised. This is normal because, well, I think this package should be improved. Probably there is a new version somewhere, so you can leave some comment on the forum, ask them for the new version. Okay, so now I have to create a new CFD study. So create study. I am into my cavity 2 folder, so I choose this folder. Let's call it cavity, and this will be case 1. Okay, right. Once you create a new project, you see in the menu you have this CFD study which appears. Now you have to unroll those menu and go into the data, and here right click and launch the GUI. So that's the way to open basically this GUI. And by default you see that you'll have a few options here. So when you click on the option here, it changes and here. And what is not obvious is that this is the pre-processing mode that you're seeing here. So if you want, for example, to check your mesh, if it is suitable for CFD, you'd use this mode. So I'll show you how to do that. Mesh selection. So the first thing is to put your mesh inside this folder, or at least tell it where your mesh is. So a good practice would be to put this med file into your mesh folder. Let's do that. It's a good practice. So let's practice the good practice, right? This is my med folder. Let's put that into your mesh folder, right? Good practice. Okay, and now it kind of glitched. Like you see, the panel just removed itself and it was placed here, and I can't open it again. So to solve this kind of problem, the only way I found is that you have to unlock those windows from this side. And now I am able to, again, to work with those. Okay, so now my mesh appears in this folder. I can open it, it appears into this menu, and I can perform a first batch calculation, which it's not real calculation because I didn't define any properties of the fluid or anything. It's just mesh quality check. So, and you just start calculation. Okay, you have to save that first. So click on this icon to save it. And start calculation. If you don't see any red here, it means it's fine. Click on OK. And even if you don't see anything here, but let me show you that inside your project, cavity 2, and I think it's no, not post, should be in your case Rusu. So that's where your results are saved. You see that you have this folder which appeared, which is contains quality type of information. So I won't show you what's inside those files. You could you could open them into Paravis. I'll show you afterwards at the end how to post-process the results, and it's exactly the same way you can post-process those mesh results. Okay, so now that I have to go switch to the calculation mode, and when you switch to calculation mode, lots more menus appear here. So that's where I'll set up basically my CFD study. So the mesh selection done already. The thermophysical model, here it's all the kind of physics that you can use in code Saturne. So I'll just use, well, I'll use none of them actually. I'll just use the steady flow calculation. So I don't need electric models, I don't need all this. Deformable mesh, I don't need that. Turbulence model, I don't need either. I think by default use K epsilon. Thermal model, I don't need. Okay, next step is to define my properties of my fluid. So fluid properties. You have already some materials defined here. Well, I'll just use a user-defined material. So water, so the rho must be 1. Just set it as 1. Viscosity, what was the value of this viscosity? 1.0, 1.0 minus 3. And the specific heat is this one. Don't forget to save from time to time. Gravity, there will be no gravity here. Volume conditions, okay, let me see. Initialization, yeah, this one is important. So initialization, this wall here will move, so I need to give him an initialization condition on the velocity. So velocity, and you see this icon is red, it means nothing has been defined. So if you click, here 0, 1, 2, this is the velocity in X, Y, and Z directions. And it can actually be defined with Python equations here, if you want. In this case, I'll keep it simple. I'll just use 0, 1 for the initialization of the velocity. Okay, and now you see this icon changed into green, which means you define that. Now the boundary conditions. So first you have to define the boundary conditions. So there's nothing in this window from the start, and we'll use the object browser here, and let's find the mesh groups, and I'll just add them. So click on your mesh group, and here click on this button, add from Salome, and you'll see that it will appear here. And do the same for the walls, do the same for the symmetry, and that's all. That's basically the 3 kind of boundary conditions you need. And here you have to double click on this to select the type of boundary condition you have. So here, this is a symmetry. Both of those conditions are walls, so I'll just leave it like that. And now in the boundary condition tab here, I have to set this as a moving wall. So click on moving wall and just check this box, sliding wall, and this is in this position. You have to give it initial velocity. So, well, it's not initial velocity, it's actual velocity. So this will be 1 meter per second. This is the velocity of my wall. Okay, now let's go into numerical parameters. Okay, equation parameters, and there are some parameters here that are basically depending on your calculation scheme that you use. For example, for the velocity here, by default, the scheme is automatic, so you choose either upwind, centered, or solu. are you centered. Some of them are more accurate but will take more time, and for example the slope test will actually do a check of the second order. I think it's written, you have a description here, or you can look in the documentation of how it works. So I'll just uncheck it here because I don't really need this, and it will be faster to solve if I uncheck this option. And now a very important part is the pseudo time step. So why is it called pseudo time step? Because this is a steady state analysis. So basically we're only calculating the last steady state. So it's not a real time dependent analysis. So basically it's called pseudo time step. It still uses some steps to calculate, but it's kind of quasi-static. It's not real time steps basically. So that's why it's called pseudo time step. Anyway, so here you need to define the time you want to calculate. So 0.1 second, and number of iteration needed. So here you need to input nth iterations. So we'll see later on how to know if the number of iterations I define here were enough to calculate the steady state. And the CFL number, so the CFL number, I think it should be defined as 8. I don't remember exactly why, so you can check the documentation or ask some questions or search on the forum if you want to know about this. Well, basically you can do some tests and see if it works. Okay, now we are done with this. The only thing is now what do we want actually to calculate? So let's go in calculation control, output control, and this is where we define the type of outputs that we'll see out of this model. In the writer, by default you have NSIDE format, so you can put it in MED format if you want. Here I'll leave it in NSIDE format, so to show you how to post-process the NSIDE format. MED format might be a bit easier because you don't have to apply as many filters, but by default let's use this. And now monitoring points. So I'll put 4 monitoring points as my model. 1, 2, 3, and 4 at various locations of this. So for example 0.25, 0.5, and if you turn them all, you see that a point has been added here. So this is my monitoring point. The second one, 0.5, 0.25. This one will be 0.5, 0.75, and the last one 0.75, 0.5. Okay, now there's one more thing to do here that I often forget about this, is to change the format to CSV. Otherwise your data will go out into a .dat text format. It's much better to have it in CSV to post-process with Paravis after. So don't forget to change this. And that's it. So let's go over the other type of thing. Now, sometimes you define those monitoring points and you don't see the result output into your result. That's because you have to go into the volume solution control and make sure that the type of result you want are monitored. So you have a check into this. Sometimes the check is removed and you don't see it. Now something else that might happen if you have a small screen is that sometimes this menu appears like that and you don't see the monitoring. So in this case, just make it bigger so that the monitoring option appears. So I've also searched for a long time to find where is this monitoring, and finally it was hidden by the menu. So in case you don't know, I'm just telling you. Okay, now let's let's set up a few profiles. So I want to export some velocity profile of my model. So for that, let's add one profile here and a second one. And the profile will be the X, so I will have two profiles. One will be X velocity along the Y-axis, and the other will be Y velocity along the X-axis. So let's click on the first profile. Let's give them a good name. So X vel along the Y-axis, center line, for example. Again, CSV. Here we only need to export it at the end of calculation. So put at the end of calculation. Now the profile is defined here into line definition. And the way to do it is to, here I have a line. So the S is the parameter, and I want it at the middle, so x.5, 0.5, sorry. Okay. Now again, my menu jumped to this place. I don't know why. Just take it out. No, sorry, jumped again. Okay, anyway. So I told you, sometimes this interface is slightly annoying. Anyway, okay, got the first one. Number of points I want, 50, because I have 50 elements. And what I want is the X velocity, so the first component of the velocity should be in this window on the right. Now let's set up the second profile, which will be Y velocity along X axis, center line 2, I think. Let me check. Yeah, okay. End of calculation, line definition. So now the parameter is X, so we put the S here, 0.5. Okay, 50 points, and this time I have Y velocity. Okay, now it's all defined. Make sure you use CSV as well, and it's done. And now the last part that remains to be done is just to calculate all of that and look at the results, hoping it will work. So for this calculation, this is very small model, so I'm using one processor and one thread, so I won't change that. Sometimes, let's say you have a bigger model and you want to calculate with more processors, so using 4 processors or something. Sometimes it can be difficult because you need to have, I think, MPI libraries installed or stuff like this. And well, anyway, I had a lot of headache setting up those things, but for this tutorial, just one processor, it works. So start calculation. Okay, start calculation, that's when I begin to pray usually. So for this kind of model, well, shouldn't have any problem. Oh yes, it works. So no red means good news. Okay. So now if I open again my cavity 2 Rusu, you have your results are saved here in this file. So what I have to do is to go into my Paravis, which is the post-processing. And Paravis, by the way, is just a wrap-up around ParaView with the added possibility to open MED files, but it's basically ParaView. So if you have ParaView installed, you can use it as well. So now let's open my results, which are into. So make sure you open the right result, cavity 2, cavity, Rusu, and in this one. In general, they are saved into post-processing, result.case. Yeah. Okay. So you see here all the results that have been saved. Click and apply. And of course, that will not appear directly. That would be too easy, right? So now the important thing to know is that you have a lot of results which are all stored into one file, and they are stored as blocks. So what you have to do is to use a filter which is called extract blocks, that will basically allow you to, oh sorry, I forgot, select fluid domain. This will allow you to separate the results. So now if you are on this filter, you see that now you are able to view pressure, velocity, results. Nice. Now you note that the result looks a bit squarey. That's because we are looking at the result at elemental results. So what I like to do usually is to add a second filter, which is cell data to point data. So this is doing some kind of approximation to the nodes, and now get much smoother results. So this is the result I want to get. Now let's change a bit the colors for this so we visualize a bit better. So go into view and open the color map editor. So this color map has a lot of options, so, and it has some presets which are nice, and I'll use blue to red rainbow. Now this is easier to view the flow in green, and personally I like to decrease the number of colors to, let's say, I don't know, 24 maybe. Maybe let's, I don't know, didn't change. Oh, okay. So now it takes some time to change. So this is the updated. Okay. So if you want to see the mesh, you can also surface with edges. Just before, let's hide it. Okay, and this is my steady state result of my model. Now let's have a look at a few more things. For example, I told you that you need to have a certain number of iteration of pseudo time steps. How do you know that your model is converged? So you can, for that, you have to open results into the monitoring. So that's why we have those monitoring points which are useful. And let's look at pressure. So probe pressure, and also, no, not X and Y. Apply. And now by default the view is this kind of view. It's Excel type, so we have to open. There is a very small button here. It took me a long time to understand this. Click on split horizontal, and the top you want is line chart view. Click on that, and now you have to go here on the left and actually activate. So let's look one by one. Let's look at the pressure first. So the curve you see here, you need first to set up the axis. So in the property window, you want the time, well, basically the pseudo time as the axis. And here in the variable, you don't want to display the time. You only want to display the 4 monitoring points, 1, 2, 3, 4 that I created. And here, just close this one. And now you can have you have a view of what happens in terms of pressure. So you see that the pressure after 400 iterations, well, more or less converge very smoothly towards this kind of value. So this is pretty fine. Let's look at velocity in X direction. So I have to go the same process. And now this is the velocity. So you see at the beginning, it kind of takes some time to reach a certain velocity value, and after this, after this amount of time, so this is I think 100 iterations, you get something very smooth. Let's have a look at Y. Okay, and similarly you get good convergence. So this means that your model is converged. If those curves, I don't know, after 400 iteration, you know, just basically diverge and do not become like that, do not converge towards a certain value, that means you either, well, you didn't define correctly your model, which is very possible, or you have to add more iteration until you reach convergence. Otherwise, the results you'll be looking at will not be your steady state results. Okay, and I think this concludes this tutorial about the cavity. I hope you learned a lot from it, and if you liked it, don't forget to subscribe to my YouTube channel. It helps a lot to know that there are people who are interested to watch those videos and put comments on the videos, and if there is something you want to see, put a comment, just let me know, or if you have some questions, don't hesitate. So thank you again for watching, and see you in the next tutorial. So if you're on YouTube, you'll probably find the link to the article and the next videos inside the description. Otherwise, you can go on my blog feaforall.com and click in the category open source FEA, and you'll find all the articles I wrote about open source FEA and the previous videos inside this category. So thank you for watching. I hope that you learned a lot and that you will learn a lot using all the videos that I am sharing on my blog. So if you like those videos, please help me to share them with your friends and other engineers. And also, please let me know what you think in the comments. It's always great to have some kind of feedback, and if you have some ideas of things you would like to learn or do with FEA, please also let me know. Thank you for watching again.